Imagine a weapon that could pierce Roman armor from 300 yards away, yet vanished from history 500 years before the crossbow was even invented. A weapon so advanced that when archaeologists first discovered its remains, they assumed it was a medieval fake. But the charred fragments tell a different story, one of forgotten engineering genius that would take humanity nearly a millennium to rediscover. But the world of ancient projectile warfare holds far more than the crossbow. Long before medieval Europe perfected the trigger mechanism we know today, ancient engineers were building bolt-firing machines that could turn the tide of entire sieges. Some were buried deep in Persian fortresses, their bronze gears still intact after 2,000 years. Others were described in texts so detailed they read like modern blueprints, designs so deadly they could punch through 3 layers of shield wall at once. These weren't crude catapults or simple bows. These were precision instruments of war, capable of accuracy that modern recreations struggle to match. These weapons are steeped in mystery, carved into history by forgotten warriors and mighty empires that dominated continents. Some were wielded by a single soldier, compact enough to carry into battle yet powerful enough to drop a charging horseman. Others required teams of engineers to operate, their mechanisms so complex that only royal armories could afford to build them. Each one represents a chapter in military innovation that history nearly erased. Today, we'll uncover 8 of the most ingenious bolt-firing weapons that came before the crossbow, each one more sophisticated than the last. And the first one? It was firing bolts in China while Europe was still fighting with bronze swords. In 1974, Chinese farmers digging a well stumbled upon something that would change our understanding of ancient warfare forever. But it wasn't the thousands of terracotta warriors that shocked weapons historians. It was what some of those clay soldiers were holding, perfectly preserved bronze trigger mechanisms for weapons that shouldn't have existed yet. Here's what makes this discovery so mind-bending. These triggers had 12 precisely fitted components. Bronze springs, catches, release pins, all working together in a mechanism so refined that it required tolerances measured in millimeters. This wasn't primitive technology. This was precision engineering from 300 BC. But here's where it gets interesting. What weapon used these triggers? The answer lay in the tomb itself. Scattered among the warriors were fragments of what Chinese archaeologists called *nu*, mechanized crossbows, but the term doesn't do them justice. These were repeating bolt launchers that predated anything similar in the West by over 1,000 years. The trigger boxes alone weighed several pounds of solid bronze, cast with such precision that modern metallurgists studying them found evidence of standardized parts. Think about that. Interchangeable components in the 4th century BC. One particular trigger mechanism, catalogued as QSH-47, revealed something extraordinary when X-rayed. Inside the bronze housing was a tri-lever system, 3 interlocking catches that controlled draw weight, hold, and release independently. This meant the operator could load the weapon, lock it at full draw, aim carefully, and release with just a few ounces of finger pressure. The mechanical advantage was staggering. Now, you might wonder how powerful these things actually were. Here's where the archaeological evidence gets brutal. Bolts recovered from Qin battle sites, solid bronze heads, 8 inches long, showed impact patterns consistent with penetrating both leather armor and the flesh behind it at ranges exceeding 200 meters. We know this because some were found still embedded in human remains, the bones showing characteristic fracture patterns from high-velocity puncture wounds. But the Qin engineers didn't stop at just making them powerful, they made them fast. The loading mechanism used a stirrup-foot brace system that let a soldier span the bow using leg strength rather than arms. This meant draw weights could exceed 300 pounds, 3 times what a human could pull by hand. One soldier could loose a bolt every 15 to 20 seconds, and texts from the period describe formations of *nu* operators firing in rotations, creating a continuous stream of bolts that ancient chroniclers compared to steel rain. Yet here's the mystery that still baffles researchers. How did this technology simply stop? After the Qin dynasty collapsed, these sophisticated trigger mechanisms largely vanished from Chinese arsenals for centuries. Some historians argue it was the cost. Each trigger box required skilled bronze casters and precision filing. Others point to the tactical shifts that favored cavalry over infantry. But the real answer might be simpler and darker. The knowledge was deliberately suppressed. The Qin were brutal conquerors, and after their fall, anything associated with their military might was systematically destroyed. What we do know is this. When these weapons returned to Chinese warfare 400 years later as the Chukaonu, they were simpler, faster, but less powerful. Something was lost in the gap. And that lost sophistication? It was about to show up somewhere completely unexpected. 2. The gastraphetes, Greece's Ballista, 5th century BC. Picture this. A Greek hoplite braces a wooden stock against his stomach, leans his entire body weight forward, and with a mechanical click asterisk, locks back a bowstring with enough force to punch through Persian bronze. This was the gastraphetes, literally Ballista, and it represents the moment Europeans discovered they could hack human limitations with engineering. The weapon's name tells you everything about how it worked. The stock had a curved end that pressed into the operator's abdomen, the gastropart, while a sliding mechanism let him use his core strength and body weight to draw back limbs far more powerful than any archer could manage by hand. It was the first European attempt at mechanizing bow power, and the Greeks stumbled onto something revolutionary: leverage. Here's the brilliant part that ancient sources barely mention but modern reconstructions revealed. The gastraphetes used a ratchet and pull system. As the operator pushed forward, bronze teeth on the slider engaged with catches on the stock, preventing the mechanism from springing back. This meant he could take his time spanning the weapon, stand up, aim, and fire, all while the bow remained at full draw. The psychological impact of this on the battlefield was immense. Imagine being a Persian archer, watching Greek soldiers casually aiming weapons that could outrange you by 50 yards, taking their time with each shot while you're desperately speed shooting to stay alive. The gastraphetes emerged around 420 BC, and ancient military writer Heron of Alexandria later described it in such detail that modern engineers have built working replicas. His specifications mentioned limbs made of composite horn and sinew, the same materials in the finest recurve bows, but mounted on a rigid stock that could handle far greater tension. Draw weights on reconstructed models range from 150 to 240 pounds, producing bolt velocities that exceed 150 feet per second. But here's what made it genuinely frightening in ancient warfare: accuracy. A hand bow is only as steady as the archer's muscles during the split second of release. The gastraphetes eliminated that variable entirely. The bolt sat in a groove, the string released from a mechanical trigger, and the rigid stock absorbed all the vibration. Archaeological evidence from siege sites suggests these weapons could hit man-sized targets consistently at 100 meters, distance where traditional archers were doing well to land arrows in a general area. Now, you might think the Greeks would have immediately mass-produced these things and dominated the Mediterranean. They didn't. And the reason reveals something fascinating about ancient military economics. Each gastraphetes required a master carpenter for the stock, a bronze worker for the trigger mechanism, and, most expensive of all, a bowmaker who understood composite lamination. Building one weapon cost as much as arming 10 hoplites with spears and shields. So the gastraphetes became a specialist's weapon, issued to elite units and used primarily in sieges where its range and penetration justified the expense. But there's a darker detail in the historical accounts that often gets overlooked. Several ancient sources mention the gastraphetes being used for asterisk execution star. The bolt's velocity and the weapon's precision made it ideal for the grim task of public punishment. A single shot from distance, clinical and theatrical at once. The fact that Greeks found a dual purpose for the weapon, both military and judicial, tells you how seriously they took its lethality. Yet for all its sophistication, the gastraphetes had a critical weakness that would limit its battlefield role: reload speed. A trained operator needed 30 to 45 seconds to span, load, and fire. Against massed infantry or cavalry, that was an eternity. The weapon was devastating for picking off officers, covering siege operations, or controlled volleys, but it couldn't match the rate of fire that traditional archers achieved. And this limitation is exactly what drove the next innovation, one that would transform the bellowbow into something far more terrifying. 3. The Oxybeles, the first bolt-shooting artillery, 4th century BC. The Greeks looked at the gastraphetes and asked a simple question: what if we made it bigger? But they didn't just scale up the design. They completely reimagined it, and in doing so, created the first true bolt-firing artillery piece in Western history. The Oxybeles, literally sharp thrower, was the gastraphetes concept taken to its logical extreme. Instead of one man pushing with his belly, the spanning mechanism required a windlass, a cranking system that let 2 or 3 soldiers slowly, methodically draw back limbs that generated tension measured in thousands of pounds. This wasn't a personal weapon anymore. This was a crew-served precision instrument designed to kill from distances that made conventional siege weapons look primitive. Here's what ancient engineers discovered when they built the first Oxybeles prototypes. Size changed everything. When you triple the length of the bow limbs, you don't triple the power, you increase it exponentially. The early Oxybeles could launch bolts, essentially spears, up to 3 feet long with enough force to pin multiple soldiers together in formation. Ancient accounts describe bolts passing through the first victim, through their shield, and into the man standing behind them. The kinetic energy was monstrous. But the real genius wasn't the power, it was the mounting system. The Oxybeles sat on a swiveling base, like a modern artillery piece. This meant crews could traverse and elevate the weapon with precision, adjusting aim by degrees rather than repositioning the entire apparatus. Bronze pins marked elevation angles, and some sophisticated models even had primitive sights, vertical posts at different distances along the frame that let operators gauge trajectory. We're talking about ballistic calculation in 350 BC. Now here's where the engineering gets almost unbelievably advanced: tension adjustment systems. Ancient sources, particularly the writings of Philon of Byzantium, describe Oxybeles models with torsion springs, twisted bundles of sinew or hair held under enormous tension by bronze frames. These didn't just store energy, they could be tuned. Tightening or loosening the spring bundles changed the weapon's power output, letting crews adjust for different ranges without changing the elevation. You wanted to hit the top of a wall 200 yards away? Tune the springs, set the elevation, and the mathematics took care of the rest. Archaeological evidence suggests these weapons achieved ranges up to 400 meters with heavy bolts, nearly a quarter mile. But here's what truly separated the Oxybeles from anything that came before. It was designed from the ground up for siegecraft. The bolts weren't random projectiles. They were purpose-built to defeat specific targets. Some had narrow, armor-piercing heads for targeting enemy artillery crews. Others had broad, chisel-like tips designed to shatter wooden siege equipment or damage fortifications. There's even evidence of firebolts, shafts wrapped with oil-soaked material that would ignite on impact. The psychological warfare aspect was equally calculated. Imagine you're defending a city wall, and you watch a 3-foot iron-tipped bolt crash through the battlements next to you. The impact so violent it splits the stone. You don't know where the next one is coming from. You can't see the crew operating the weapon. Every time you show yourself above the wall, you're gambling that you're not in someone's crosshairs 300 yards away. Ancient siege accounts describe defenders abandoning sections of wall entirely after targeted Oxybeles fire killed enough officers to break morale. But despite their effectiveness, the Oxybeles had one massive limitation that prevented them from becoming the dominant siege weapon: construction complexity. Each weapon required a master carpenter to build the frame, a bronze caster for the spring housings and trigger mechanisms, and specialized knowledge of torsion physics that only a handful of engineers in the ancient world possessed. The springs themselves, twisted animal sinew, had to be prepared in specific humidity conditions or they'd lose tension. Climate mattered. Too dry and the sinew would crack. Too humid and it would stretch. Maintaining these weapons in the field was a nightmare. And yet, armies kept building them, kept deploying them, because when they worked, they were unstoppable. Before moving on, I'd like to ask you for something. If you enjoy these deep dives into forgotten military technology and want to support this channel, please consider subscribing. It's free. Now, the Greeks weren't the only ones developing sophisticated bolt throwers. Halfway across the world, another civilization was perfecting a weapon that would make the Oxybeles look almost quaint by comparison. 4. The Roman Scorpio, empire-building precision, 1st century BC. When Roman engineers encountered Greek artillery, they did what Rome always did best. They stole the concept, improved the manufacturing, and deployed it at industrial scale. The Scorpio wasn't just a Roman copy of the Oxybeles. It was a complete redesign focused on one principle: repeatability. The name itself is telling. Scorpio, scorpion, because the weapon sat low to the ground with its bolt track angled upward like a tail ready to strike. But unlike its Greek predecessors, the Scorpio was designed for mass production. Roman military records indicate that a single legion, about 5,000 men, carried 60 Scorpios as standard equipment. That's one precision bolt thrower for every 83 soldiers. No ancient army had ever deployed artillery at that density. Here's what made that possible: standardization. Roman engineers created modular components. The torsion springs used iron frames instead of bronze, cheaper and easier to manufacture. The wooden stocks followed patterns so precise that replacement parts from one Scorpio would fit another. Archaeological finds from Roman frontier forts show warehouses full of pre-cut timber, bundled sinew, and iron fittings, ready to assemble artillery kits that could replace damaged weapons in the field within hours. But the Scorpio's real innovation was tactical flexibility. Unlike the massive Oxybeles that required a prepared position, the Scorpio was mobile. 2 men could carry the disassembled weapon, stock, springs, and mount, and have it operational in under 15 minutes. This meant Roman commanders could reposition artillery during battle, concentrating fire wherever the enemy line showed weakness. Ancient accounts describe Scorpio crews advancing with infantry, setting up behind the front lines, and providing suppressive fire that pinned defenders in place while legionaries closed for melee. The bolts themselves reveal Roman engineering obsession with optimization. Standard Scorpio ammunition was an iron-tipped wooden shaft, 27 inches long, weighing about 1 pound, light enough to achieve flat trajectory but heavy enough to retain energy at range. The iron heads came in variations: bodkin points for armor penetration, broadheads for soft targets, and incendiary tips that could be wrapped with pitch-soaked cloth. One excavation at Maiden Castle in Britain uncovered a defender's skeleton with a Scorpio bolt lodged in the spine. The iron point had entered between the shoulder blades and traveled downward through the ribcage. The angle of entry suggests the shot came from 150+ meters away. Now, here's the detail that really shows Roman tactical thinking: the sighting systems. Later Scorpio models had graduated bronze scales mounted on the elevation mechanism. These weren't decorative. They were range-finding tools calibrated to the weapon's ballistic arc. A trained crew could dial in distance by setting the elevation pin to a specific marking, and multiple Scorpios could be aimed at identical settings to create focused fire zones. Ancient military manuals describe techniques for walking Scorpio fire across enemy formations, each salvo hitting a few meters further than the last, forcing defenders to either advance into the impact zone or retreat under pressure. But the Romans discovered something unexpected about massed Scorpio fire: sound. When 10 or 20 Scorpios released simultaneously, the combined **crack** of the torsion springs and the whistle of bolts in flight created a distinctive noise that ancient writers compared to thunder. This acoustic signature had psychological impact. Defenders couldn't see individual bolts in flight, but they could hear the salvo coming, a split-second warning that was almost worse than no warning at all. The anticipation broke formations. Yet for all its sophistication, the Scorpio had vulnerabilities that clever enemies learned to exploit. The torsion springs were the weak point. Sinew bundles under thousands of pounds of tension were prone to catastrophic failure, especially in wet conditions. A single overstressed spring could explode, sending bronze shrapnel into the crew. Roman maintenance protocols required springs to be inspected daily and replaced every few weeks of active use. This created a logistics tale. Every legion needed wagons full of spare sinew, tools, and trained artificers who could rebuild springs in the field. And then there was the human factor. Operating a Scorpio required genuine skill. The spanning windlass needed coordinated cranking or the springs would load unevenly. The trigger mechanism, a bronze sear under enormous tension, could catch fingers if released improperly. Training manuals from the period indicate that Scorpio crews underwent months of practice, and battlefield records show that experienced artillery teams were valued specialists, often exempt from frontline combat duty to preserve their expertise. But here's what really set the Scorpio apart from earlier bolt throwers. The Romans used them for **counter-battery fire. When facing enemies with their own artillery, Roman crews would target the opposing weapons first, trying to kill the operators or damage the mechanisms. Ancient accounts describe artillery duels at sieges, Scorpios versus ballistae, crews desperately reloading while bolts whistled overhead. This was probably the first time in military history that ranged weapons regularly fought other ranged weapons, a tactical evolution that wouldn't be matched until gunpowder artillery emerged. The Scorpio remained in Roman service for over 400 years, a testament to its design. But as effective as it was, the Romans weren't the only empire refining bolt-thrower technology. Far to the east, Chinese engineers were about to perfect something that would make even the Scorpio look primitive. 5. The Chokao-nu, China's repeating devastation, 1st century ad. Imagine a weapon that could fire 10 bolts in 15 seconds, without reloading. Not rapid single shots, but a continuous stream of projectiles that could shred advancing infantry before they closed to melee range. This was the Chokao-nu, and it represented a quantum leap in ancient weapons technology, the world's first practical repeating crossbow. But here's the part that makes historians argue. We're not entirely sure when it was actually invented. Ancient Chinese texts reference continuous crossbows as early as the 4th century BC, but the first reliable descriptions with mechanical details don't appear until the Han Dynasty around 200 AD. What we do know is that by the time the weapon was widely documented, it had been refined into something genuinely revolutionary, a bolt thrower that prioritized rate of fire over raw power, and in doing so, changed infantry tactics. The mechanism was almost absurdly simple, which is probably why it worked. A rectangular magazine sat on top of the weapon, holding 10 bolts stacked vertically. When the operator pulled a lever backward, 3 things happened simultaneously. The bowstring drew back, a spent bolt fell away, and gravity dropped a fresh bolt from the magazine into the firing groove. Pushing the lever forward released the string, fired the bolt, and the cycle repeated. No separate loading action. No fumbling with ammunition. Just pull, push, pull, push. Continuous fire as fast as the operator could work the lever. Now, before you think this sounds too good to be true, here's the catch: power. The Chokao-nu sacrificed draw weight for mechanical simplicity. Most models had bow strength around 80 to 100 pounds, roughly half that of a standard military crossbow. This meant effective range was limited, maybe 70 to 80 meters maximum. The bolts were shorter too, basically heavy darts rather than true crossbow quarrels. They wouldn't punch through armor at distance. But that limitation was the entire point of the weapon's design. The Chokao-nu wasn't meant for long-range sniping. It was an area denial weapon, designed to turn infantry formations into killing zones at close to medium range. Ancient tactical manuals describe Chokao-nu operators positioned in formations 3 or 4 ranks deep. The front rank would fire their 10-bolt magazine, then rotate to the back to reload while the next rank fired. This created rolling volleys, a continuous stream of projectiles that didn't have to be accurate to be devastating. Volume of fire mattered more than individual shot precision. And here's where the tactical innovation becomes clear: suppression. Modern military theory talks about suppressive fire as a force multiplier, keeping enemy heads down, disrupting formations, creating chaos. The Chinese understood this concept 1,800 years ago. A group of Chokao-nu operators didn't need to kill everyone in an enemy formation. They just needed to fill the air with enough bolts that advancing troops either slowed down, broke formation to find cover, or bunched together, making themselves better targets for follow-up volleys or cavalry charges. Archaeological evidence shows these weapons were produced in staggering numbers. Excavations of military depot sites from the Song dynasty have uncovered literally hundreds of Chokao-nu components, stocks, bow limbs, magazines, all showing signs of mass production. The manufacturing techniques used molds for bronze components and jigs for wooden parts, allowing relatively unskilled workers to assemble weapons quickly. This was military-industrial complex thinking before the Industrial Revolution. But there's a detail in the historical records that reveals just how effective these weapons were: the antidotes. Chinese military treatises specifically describe defensive formations and shield tactics designed to counter Chokao-nu fire. The fact that armies needed specialized counters to this one weapon tells you how much of a battlefield problem it became. Some defenses involved large wickerwork shields that could catch bolts without weighing down troops. Others used smoke screens, burning damp plant material to create visual cover that made aimed fire impossible. Now here's where the weapon's limitations became fatal flaws against certain enemies. The Mongols. Mounted archers presented a nightmare scenario for Chokonu operators. The weapon's relatively short range meant Mongol cavalry could circle beyond effective engagement distance, peppering Chinese formations with arrows while staying safe from return fire. The Chokonu's rapid-fire advantage evaporated when the enemy simply didn't close. Chinese military records from the 13th century show declining use of the weapon precisely as mobile cavalry warfare dominated the steppes. But before the Mongols ended its battlefield dominance, the Chokonu had one more moment of terrifying effectiveness. During the siege of Xiangyang, 1268 to 1273, defenders used Chokonu fire to devastating effect against Mongol assault troops trying to scale the walls. The confined space negated the weapon's range limitation, and the rapid fire was perfect for crowded siege conditions. Historical accounts describe bodies piled at the wall base, many showing multiple bolt wounds, evidence of the weapon's volume of fire capability. The siege lasted 5 years partly because the Chokonu made wall assaults so costly. Yet for all its tactical innovation, the Chokonu was eventually abandoned as military technology moved toward more powerful single-shot crossbows and, eventually, gunpowder weapons. But its core concept, trading power for rate of fire, would echo through weapons design for the next 1,000 years. And speaking of trading power for other advantages, the next weapon took a completely different approach, making the operator nearly invisible. 6. The Archabalista, Rome's mobile sniper, 2nd to 3rd century AD. While most Roman artillery grew larger and more complex, one weapon went the opposite direction. The Archabalista was Rome's attempt to create a one-man bolt thrower that combined the Scorpio's precision with something no previous artillery piece had: true portability. This wasn't a crew-served weapon. This was a sniper's tool. The name itself is a hybrid, arcus meaning bow and ballista meaning thrower, and the weapon was exactly that fusion. Ancient sources describe it as small enough for a single soldier to carry assembled, with a draw mechanism that one person could operate. Modern reconstructions based on archaeological fragments and Roman engineering texts suggest a weapon weighing around 15 to 20 pounds, roughly comparable to a modern rifle. But here's what made the Archabalista genuinely innovative: the spanning mechanism. Instead of the windlass cranks required for larger artillery, the Archabalista used a stirrup lever system similar to later medieval crossbows. The operator would place one foot in a stirrup at the front of the weapon, grip the bowstring with a specialized hook attached to his belt, and stand up, using his entire body weight and leg strength to draw the bow. This meant one person could span a weapon with draw weight exceeding 200 pounds, generating bolt velocity comparable to much larger Scorpios. Now, you might wonder how Roman engineers managed to fit that much power into such a compact frame. The answer was in the spring design. The Archabalista used torsion springs, but scaled down and refined. Instead of the massive iron frames on a Scorpio, the Archabalista had compact bronze spring housings barely larger than a clenched fist. The sinew bundles were thinner but twisted to higher tension, and the entire mechanism was encased to protect it from weather and damage. One partially preserved example from a Roman fort in Britain shows bronze housings with threaded adjustment screws. The operator could tune spring tension in the field. And here's where this weapon gets interesting from a tactical perspective. It was designed for assassination. Roman military manuals from the period describe Archabalista operators as speculator, scouts and specialist troops who operated independently from main formations. Their job was to target high-value enemy combatants, officers, enemy artillery crews, messengers, anyone whose death would create tactical advantage. The weapon's range, around 150 meters for accurate shots, let them engage from distances where they were difficult to spot or counter. Archaeological evidence backs this up in a grim way. Several excavations of Roman frontier battle sites have uncovered enemy skeletons with distinctive wound patterns. Single bolt impacts to the head or torso, often at angles suggesting the victim was shot from elevated positions or from concealment. These weren't battlefield casualties from massed fire. These were deliberate, aimed kills. The Archabalista was Rome's precision instrument for decapitation strikes, literally and figuratively. But the weapon's compact size created unexpected problems. The smaller torsion springs were more prone to failure than larger artillery springs. The higher tension-to-volume ratio meant the sinew bundles degraded faster, especially in wet climates. Roman maintenance records indicate that Archabalista operators carried spare spring assemblies as standard equipment, and field repairs were common. Unlike the Scorpio, which might operate for weeks between maintenance, the Archabalista needed near-constant attention to remain combat effective. Then there was the ammunition challenge. Standard Scorpio bolts were too heavy for the Archabalista's lighter draw weight. So Roman artificers developed a specialized bolt, shorter, lighter, with a narrow armor-piercing head designed to maximize penetration rather than deliver massive impact energy. These bolts were expensive to manufacture. Each iron head required skilled forging to maintain the precise balance needed for accurate flight. An Archabalista operator couldn't just grab ammunition from the general supply. He needed purpose-made projectiles. Now here's the detail that reveals how seriously Rome took this weapon: the training. Becoming an Archabalista operator required not just technical skill with the weapon, but fieldcraft, camouflage, stalking, observation. Ancient sources mention specialized units of these troops attached to frontier legions, operating in small teams to harass enemies and provide intelligence. They were force multipliers, individual soldiers who could project lethal force at distances that turned them into asymmetric threats. But despite its effectiveness, the Archabalista never achieved widespread deployment. The reason was simple economics. Each weapon required precision manufacturing that cost several times what it took to arm a regular legionary. The training investment was enormous, and the specialized ammunition added logistical complexity. Roman military planners did the math and concluded that for the cost of equipping one Archabalista operator, they could field multiple Scorpio crews with better sustained fire capability. Yet the weapon remained in service for specific roles: frontier scouting, siege operations, protection of high-value positions, until the late Empire period. And it represented something important in weapons evolution: the recognition that sometimes the most effective tool isn't the most powerful, but the one that's in the right place at the right time. But while Rome was perfecting precision bolt throwers, another civilization was taking the artillery concept in a completely different direction, towards something so massive it would redefine siege warfare. 7. The polybolos, the first automatic artillery, 3rd century BC. In the endless arms race of ancient siege warfare, Greek engineers asked a question that would lead to one of history's most extraordinary and most impractical weapons. What if we made artillery that fired itself? The polybolos, described in detail by the engineer Philon of Byzantium around 200 BC, was theoretically the world's first automatic weapon. Not semi-automatic, not rapid-fire. Fully automatic, a bolt-shooting machine that could theoretically sustain continuous fire as long as someone turned a crank. And if that sounds too advanced to be real, well, historians argued about that for centuries. Here's what Philon's treatise actually describes: a weapon with a chain-drive magazine system. The basic concept used a modified Oxybeles frame, but instead of manually reloading after each shot, the polybolos had a flat chain-link conveyor mounted above the firing track. This chain held multiple bolts in individual slots. When the operator turned a windlass crank, the mechanism simultaneously did three things: drew back the bowstring, advanced the chain to position a fresh bolt, and released the previous shot. In theory, the cycle repeated continuously. One crank rotation, one bolt fired. Now, before we get too excited about ancient machine guns, here's the reality check that modern reconstructions revealed. Building a working polybolos is extraordinarily difficult. The chain drive needs to be perfectly synchronized with the draw mechanism, or bolts jam, misfire, or fall out of the magazine. The windlass requires tremendous force to operate, drawing back torsion springs powerful enough to launch bolts while also fighting the friction of the chain mechanism. Modern engineers who've attempted reconstructions report that one person can't operate the crank effectively. You need at least two people on the windlass, working in coordination, to sustain fire. And the rate of fire? Not exactly a machine gun. Realistic modern reconstructions achieve maybe one shot every 10 seconds under ideal conditions with a trained crew. That's actually slower than a well-drilled Scorpio crew doing manual reloads. So why build this mechanically complex weapon if it doesn't fire faster than simpler alternatives? The answer reveals something interesting about ancient military thinking. suppression, and psychological warfare. What the polybolos lacked in rate of fire, it potentially made up for in consistency. A manual reload involves gaps, moments where the weapon is clearly not ready to fire. The polybolos, even at slow fire rates, could theoretically maintain continuous pressure. Defenders wouldn't see the crew frantically reloading. They'd just see an artillery piece that seemingly never stopped shooting. The psychological impact of facing an unstoppable weapon could be worth the mechanical complexity. But here's where the historical record gets frustrating. We don't actually know if the polybolos was ever built in quantity. Philon's treatise reads like an engineering proposal or prototype documentation, not a description of deployed military equipment. No archaeological evidence has ever confirmed the existence of polybolos fragments at battle sites or in ancient armories. Later Roman and Greek military writers mention other artillery types but never reference the polybolos specifically. This suggests the weapon may have been a fascinating design exercise that never saw real combat use. Yet that doesn't mean it was impossible or impractical, just expensive and difficult. Modern materials science analysis of Philon's specifications indicates the weapon would have required precision bronzeworking beyond what most ancient city-states could afford. The chain mechanism alone needed dozens of individually forged links, each with pins and connectors that had to fit within tight tolerances or the whole system would jam. The cost-to-benefit ratio probably killed the project before it reached battlefield deployment. But there's evidence the core concept influenced later weapons. Byzantine military manuals from the 10th century AD, over 1,000 years after Philon, describe artillery with magazine feeding systems and mechanical cocking mechanisms. These weren't identical to the polybolos, but they shared the same basic insight: mechanize the reload cycle to sustain fire. The knowledge didn't die completely. It just went dormant until manufacturing techniques caught up with the design ambitions. Now here's the fascinating what-if that historians love to debate. What if the polybolos had been perfected? If ancient engineers had solved the synchronization problems and made the mechanism reliable enough for field use, siege warfare could have evolved very differently. Automated artillery that could sustain fire would have forced changes in defensive architecture, in assault tactics, in the entire calculus of siege operations. But that didn't happen. The polybolos remained a might-have-been, a road not taken in weapons development. And that brings us to the last weapon on our list, one that combined everything ancient engineers had learned about bolt throwers and pushed the technology to its absolute limits. 8. The ballista, the ultimate evolution, 1st century BC, 5th century AD. If every previous weapon we've discussed was an experiment in bolt-throwing technology, the ballista was the perfected final form. This wasn't just scaled-up artillery, it was a weapon system optimized through centuries of warfare into something that would dominate siege tactics for over 500 years. The name ballista gets thrown around casually in history, but that's actually misleading. There wasn't one ballista design. There were dozens, each tailored for specific tactical roles. But they all shared core features: massive torsion springs, precision engineering, and the ability to launch projectiles, both bolts and stones, with devastating accuracy at ranges that defied belief. Here's what separated the ballista from earlier weapons: manufacturing sophistication. Roman engineers developed mathematical formulas for ballista construction based on the diameter of the spring holes. Everything, frame dimensions, arm length, draw weight, projectile size, scaled proportionally from one number. This meant engineers could design ballistae of any size with predictable performance characteristics. Want a weapon that throws 5-pound stones 400 meters? The math told you exactly how big to make the spring housings. Need a bolt thrower for urban siege work? Run the formula in reverse. And these weren't theoretical calculations, they worked. Archaeological excavations at Marzada uncovered ballista stones still showing chisel marks where Roman engineers carved weight measurements and range data directly into the projectiles. They were calibrating their artillery through live-fire testing and recording the results. Ancient quality control that modern engineers recognize immediately. But here's where ballistae became genuinely terrifying: the diversity of ammunition. Standard loadout included 2 projectile types: iron-tipped bolts, 3 to 4 feet long, for anti-personnel work and targeting enemy artillery, and carved stone spheres, 5 to 10 pounds each, for structural damage and area bombardment. But battlefield archaeology shows they used far more than just those basics. Incendiary projectiles wrapped in pitch-soaked cloth. Lead balls that would fragment on impact, creating primitive shrapnel. Multi-headed bolts designed to tumble through formations. Even biological warfare, clay pots filled with scorpions or venomous snakes, launched over walls to create chaos. The versatility made ballistae the artillery equivalent of a Swiss army knife. Now, the power levels these weapons achieved border on absurd by ancient standards. The largest ballistae, called onagers by some Roman sources, though that term technically refers to a different weapon, could launch 100-pound stones. Reconstructions based on ancient specifications suggest these megaballistae generated impact energy exceeding 100,000 joules. For comparison, a modern .50 caliber rifle generates about 18,000 joules. We're talking about weapons that hit like modern artillery shells, built with wood, bronze, and twisted animal sinew. And the damage they caused was documented in brutal detail. The siege of Jerusalem in 70 AD saw Roman ballistae in action on both sides. Defenders had captured Roman artillery and turned it against the besiegers. Josephus, who witnessed the siege, describes ballista stones decapitating multiple soldiers at once, crushing siege towers, and punching holes through city walls that required emergency repairs. One particularly gruesome account mentions a defender's head being struck by a ballista stone and launched 3 furlongs, over 600 meters, by the impact force. But the real sophistication shows in how Romans deployed these weapons tactically. Ballistae weren't just siege tools, they were integrated into legion tactics. Standard legion deployment included artillery sections positioned to provide overlapping fields of fire, protecting infantry flanks and disrupting enemy formations before engagement. Ancient military manuals describe techniques for using ballista fire to shape the battlefield, denying certain approaches, channeling enemy movement, creating zones where advance was suicidal. And then there was counter-battery fire. Just like with the Scorpio, ballistae engaged in artillery duels, crews trying to destroy enemy weapons or kill their operators before being destroyed themselves. Ancient accounts describe almost modern-sounding scenarios, ranging shots to find distance, bracketing fire to zero in on targets, concentrated fire from multiple weapons to overwhelm defenses. This was systematic, calculated warfare using mathematics and engineering to project force at standoff range. But for all their power, ballistae had the same fundamental weakness that plagued all torsion artillery: maintenance. The sinew springs were temperamental, requiring constant adjustment and replacement. Humidity affected tension. Temperature changes degraded performance. Campaign records show legions carrying massive logistics trains of spare parts, replacement sinew, specialized tools, and trained engineers who could rebuild entire weapons in the field. A legion's ballista battery might be devastating, but it came with a supply tail that stretched for miles. And there's one more limitation that eventually doomed the ballista as a weapon system. It was too good at what it did. By the late Roman Empire, defensive architecture had evolved specifically to counter ballista fire. Walls became thicker, with sloped faces that deflected projectiles. Fortifications used multiple curtain walls to absorb bombardment. Defenders built covered positions that artillery couldn't reach. The arms race between offensive and defensive technology eventually reached a stalemate where ballistae remained effective but no longer decisive. Then gunpowder arrived, and everything changed. Cannons didn't immediately replace ballistae. Early gunpowder weapons were actually less reliable and less accurate than mature torsion artillery. But cannons had one insurmountable advantage. They didn't require exotic materials or specialized artisan knowledge to build and maintain. Gunpowder and metal were simpler supply chains than sinew, bronze precision casting, and centuries of accumulated engineering expertise. By the 15th century, the ballista was extinct as a military weapon, its knowledge base scattered and largely lost. Modern attempts to reconstruct ballistae rely on fragmentary ancient texts and archaeological guesswork. We'll probably never know exactly how powerful the best ancient examples actually were. But what we do know is this: for over 500 years, torsion artillery represented the peak of human ability to project lethal force at range without gunpowder. These weren't primitive war machines. They were sophisticated weapon systems that required mathematics, metallurgy, materials science, and tactical doctrine to employ effectively. And every one of them came before the crossbow was even invented. If you found this journey through ancient weapons technology fascinating, consider subscribing. There's a lot more history that's been forgotten than most people realize.